All right. And okay, by the way, before I look at your answers, okay, so the question asks you to, I'll read the question for you. Answer the following questions based on this submicroscopic representation. In the submicroscopic representation, you have a system with two phases, gas and the liquid. There's no solid. Okay, that's what's given to you. Now, the first question is, which phase do you expect to have the strongest intermolecular forces? Okay, most of you said solid. It would have been correct if we had a solid in the system, but based on the representation, which we don't have a solid, okay, it cannot be your answer. It must be the liquid. Okay, so the point is this. Please read the question. I have seen time and again people do not, people miss questions because they just do not read the questions carefully. Okay, please get used to reading them. And this is one example. I want to keep it like this so that, it reminds me to tell you to remind you to read the questions. Too many reminders there, right? You get the point. Okay, so please read the questions, especially during what is happening this Friday, which is going to be so much fun. Please read the questions. Okay. All right. The phase with the highest potential energy, wonderful. Most of us said gas. That is correct. Why? We have the weakest attractive interactions. Weakest attractive interactions means highest potential energy. Okay. And then phase with the highest average kinetic energy. Most of us remembered that the kinetic energy, average kinetic energy is set by the temperature because everything is at the same temperature regardless of the phase or the mass. They will all have the same average kinetic energy per particle. And then the last question, I believe, is about the vapor pressure, the substance with the highest vapor pressure. Most of you recognize it is nitrogen, and that is correct. But why? How do you know that? Just to make sure we are on the same page. Why did you select nitrogen? Can I have a volunteer? I know everybody wants to do that. Hey, Harshini, can you get somebody? I just want to talk with somebody. Anybody? Everybody wants to talk. I know. Go ahead.
There's somebody behind. Someone behind there.
Oh, okay, perfect. Lila. Okay. Can I have the microphone with Lila, please? Peyton, do you have a microphone by any chance? No?
Yeah.
All right, Lila, what did you pick nitrogen?
Yeah.
Why?
Well, with higher IMFs, it means the vapor pressure is lower. So with higher vapor pressures, that means the IMF is low.
That is correct. But how do we know nitrogen has the lower IMF or weak IMF?
Well, because nitrogen here is a gas, that means it has a low IMF, high, what's it called?
High
EP.
potential energy. Okay.
Yeah.
Uh-huh. All right. But the thing is, there are other gases in there as well, right? Why you pick nitrogen out of them? There's carbon dioxide there, there's oxygen there, there's nitrogen, and there's water. Why nitrogen? This is really important that you think about this. Okay. Why nitrogen out of all those gases in the gas phase?
There's more nitrogen in the gas phase than the
More nitrogen. More particles of nitrogen means, get this, remember the particular model of matter? Okay? More collisions with the walls of the container. More collisions means higher pressure. Remember the pressure is due, thank you, Lila, I appreciate that, okay? The pressure is due to collisions between the particles and the walls of the container. If you have more particles, okay, more collisions means more pressure. That's how we know nitrogen must have the highest vapor pressure. Please, that train of thought, okay, it should flow like that, okay? More particles means more collisions with the walls, meaning more pressure. That should be the way you think about this. All right, what questions, concerns, comments do we have at this point? Okay. I'll reopen the question especially for the intermolecular force strength one, the first one. Switch that liquid, and then we will move on to the highlight of today's lecture. Is this? All right, learning assistants, are you ready for this? Yeah? All right, look at that. Okay. So most of us picked gas. Okay. And then the second most popular answer is C, because some of us thought that this is kind of a trick question, so went with that. And then four of us picked the right answer. Okay. All right. Yeah. So again, this is the highlight for today's lecture. Okay. This is we're gonna change the way we look at the world, to think about things. All right. This is good. All right. Any of those four students who picked liquid, can you enlighten us? I mean, anybody who picked, I mean, who had liquid, why did you pick liquid? Please, we want to know. Thank you. All right. What's your name, sir?
Tyler.
Go ahead.
So they obviously they have the same temperature, so they have the same kinetic energy.
Average
Kinetic energy. So the speed's going to be dependent on which particle is the lightest.
Lightest?
Yes, because lighter particles with the same amount of kinetic energy will move faster. And that is not the lightest. So.
Wonderful. Thank you, Tyler. Yes, exactly. Okay. Tyler's point is we have the lightest particles in the liquid. Okay. They must be moving the fastest. It's just like the Nikola truck, 18-wheeler versus the Tesla car again. Right? Tesla car moves faster with the same kinetic energy. Okay. Now, here's the thing though. How, Tyler, if I may come back to you, how do you know that liquid phase has lightest particles? Can I have the microphone with Tyler one more time? Peyton, can you? How do you know that?
I use the periodic table.
Oh, okay. It's getting complicated. No, it's okay. Yeah. So we're gonna get there too. Okay, Tyler, you don't need me today apparently, but anyway, that's fine. Just hang in there. Maybe I might be able to, show you a few tricks of my cups as well. Okay. Anyway, here's the information needed for this. Nitrogen, this is N2, has a relative mass of 28. Okay. Oxygen, on the other hand, O2, has a relative mass of 32. And here's carbon dioxide, okay, CO2. It has a relative mass of 44. On the other hand, the liquid is made of mostly H2O. Okay, H2O has a relative mass of 18. So out of all the particles, H2O are the lightest. Therefore, with the same energy, same kinetic energy, they must be moving the fastest. That's the idea there. Okay. All right. Now, here's the learning goal for today. The first learning goal for today. We will learn how to determine the mass of any given particle. Learning objective number 1. Okay. Let's see, how long will it take for us to achieve that objective? Okay. Well, but for now, I'm going to reopen this. We have the fastest moving particles in the liquid phase because they're the lightest particles. But we will decide how to determine the mass of any given particle. All right. So I'm going to clear my doodling. So here's the problem though. These particles we are talking about are so tiny, okay? We cannot catch an oxygen particle from the air and, keep it on a balance or a scale and get the mass of those particles. We cannot do that, okay? So it's like this, okay? Here's a hypothetical experiment for us to do. So now that Halloween is almost near, right? So say that you want to know how much more massive a Skittle is compared to an M&M. Skittles is bigger and M&M is smaller. Okay. So you want to know that using a kitchen balance, which is like old school. Problem is the kitchen balance cannot tell you the mass of one Skittle or mass of one M&M. What can you do? You want to know how much more massive a Skittle is compared to M&M, but the kitchen balance cannot register the mass of one Skittle or one M&M. How can we solve this problem? Go ahead. I'll give you 1 minute. What can we do?
Right? Yeah. For example. Okay. That's brilliant. Good. Keep going. You're on the right track. What else? I don't know. I'm just asking if there's. So what he said is you want to find out how much more kilo is compared to the weight of an eminence. But if you just place one scale on a kitchen scale, you cannot measure that small of a weight. No. So what would be a brilliant way or better measure how much?
Let's see. How can we solve this problem? Do I have anyone to talk with? Anybody? How can we solve this problem? Harshini, are you still there? Do you have a microphone? Thank you. Wonderful. What's your name, sir?
My name's Aiden.
Aiden, go ahead.
I said you could add like 50 Skittles on the thing and mass out 50. And then from that mass, you would divide it by 50. So you could get just the mass of one.
Okay, so in other words, you can, even though you cannot measure the mass of one skittle, you can measure the mass of more than like 50 skittle.
Yeah.
So you get that mass, and then you get the mass of 50 M&Ms too, and then you divide the mass of 50 skittles by the mass of 50 M&Ms. Yeah, and that should give you the how much more massive the skittle is compared to M&M.
Yeah.
Yeah. Okay, one more time. So what you do is you measure not the mass of just one skittle, but 100 skittles or 50 skittles. Okay. And also you measure the mass of 50 M&M. Okay. And then you divide the mass of 50 skittles by the mass of 50 M&M. That should be how much more massive a skittle is compared to an M&M. Yeah. So that's going to be the approach. Now that's going to be the same approach we'll be using when it comes to these tiny particles as well. Now, here's the problem though. How can we get 50 tiny particles? Yeah. Okay. How can we get the same number of, say, like oxygen and nitrogen, or maybe helium, neon, or argon? Okay. To think about that, I want you to tackle this problem. Here we go. These are noble gases. Okay. Do you know why we call them noble gases? They're kind of inert. They don't want to interact with anything else. Okay. Therefore, I mean, they're inert. I mean, so for that reason, they are called noble gases. Okay. And they are the gases that act closest to the ideal behavior. Why? Ideal behavior means particles don't interact with each other. Okay. Now, anyway, so that's a side story. The idea is, the ideal gas law can be easily applied for these guys. Okay. So what does the ideal gas law say? We have pressure, volume, okay, is equal to the number of particles, a constant, a Boltzmann constant, times T. Meaning, number of particles is pressure times volume divided by a constant and T. Okay. So you are told that each balloon has a volume of this. So they are the same. All the balloons have the same volume. And all the balloons have the same pressure. And all the balloons have the same temperature of 298 Kelvin or 25 degrees Celsius. Okay. And the Kb is a constant. Therefore, it is not going to change as well. So all of the balloons have the same pressure, same volume, same temperature, and same constant, meaning they should all have the same number of particles as well. Okay. So the N, or the number of particles in all the balloons, are the same, regardless of their size or the mass. All right, I'll let you think about this for 30 seconds, and then we can talk about this. Go ahead.
When he's referring to the gas law, so the fact that you know that the constants are all there,
I wrote the question. I give in case somebody wants to revise the answers, I've reopened the question as well. Questions, concerns, comments do we have at this point? Any questions, concerns, comments? Okay. Now, here's what we have done so far. So, if you can pay attention for a few minutes, please. Okay. So we have to get the same number of particles of three substances here: helium, neon, and argon. Okay. Do you have a question, sir? Yeah, we have a question over here, Peyton. Give me your name, sir, one more time.
I'm Ronaldo. And
Ronaldo?
Ronaldo, yes.
Yeah, Ronaldo.
So my question is for the atomic number, I guess, between this,
I don't know what that is.
or I guess the little number on the periodic table for each element.
For the moment, I have no idea what that is. For the moment, let's say.
All right, sure. So if we asked a different question, for example, which balloon would have more particles in it, would you do helium?
No,
Okay.
they have the same number of particles.
Okay,
N is the number of particles. They're the same.
okay.
It doesn't matter what their masses are, they're going to have the same number of particles because they tend not to interact with anything.
Yeah, can we?
Okay. But if you have real gases or the other gases, they will deviate slightly from ideal gas behavior. Okay. But especially under some conditions, they're going to be more ideal than other conditions. But it's a different story, but it's not relevant to this.
Oh, okay. Sorry.
No, that's okay. That's okay. But yeah. Any other questions, concerns, comments though? All right. Now here's the thing. We have the same number of helium particles, neon particles, and argon particles. Okay. Now, how did you do that? By getting the same pressure, volume, and temperature for all these balloons, we were able to do that. Now, that's beautiful. Okay. If we weigh these balloons, okay, so these balloons registered these weights. Helium balloon was 4 grams, neon was 20, and argon was 40. If somebody asks you how much more massive neon is compared to helium, what would you say? How many times? 5 times. How do you know? Okay. Yeah. Helium is 4. Neon is 5 times that, right? 5 times 4 is 20. Okay. Therefore, neon is 5 times more massive than helium. In a different way, we can say the same thing like this. The relative mass of neon is 5 with respect to helium. Okay. Relative mass is 5 for neon with respect to helium. Now, your turn. Can you determine the relative mass of argon with respect to helium? Go ahead. Any questions about the idea of relative mass? Okay, mass of something with respect to, something else. That's the idea there. Any questions, concerns, comments? Okay. Now, here's the next thing we want to do. Yeah, the mic's acting up today, so don't worry about it too much. It's fine for the moment. We need to try to stay away from the speakers. Sometimes, yeah. All right. Thank you, Nathan. Anyway, so actually, we have already information about all the relative masses of elements, okay, in a beautiful arrangement called the periodic table. Okay. If you go to any periodic, not any periodic table, okay, most of the correct periodic table, they should have a number under each symbol, element symbol. And that number gives you the relative mass of that atom, that element. Okay. For example, for hydrogen, you see 1.008. That's the relative mass of hydrogen. Okay. And for helium, it is 4.0. And for carbon is 12, neon is 20.18, and oxygen is 16, and so forth. Quick question. Does anybody know with respect to what? With respect to mass of what? Yes, sir. Can I have the Harshini? Thank you, Harshini. All right. What's the name, sir?
Isaac,
Isaac, go ahead.
I believe it's in respect to a carbon 12 atom.
Great, very close. Okay. All right. So because you started with that, okay, I'll run with that. Okay. So that mass is with respect to, get this, Isaac, 1/12 of the mass of carbon 12 isotope. Okay. But here's the thing though, 1/12 of the mass of carbon 12 is very close to the mass of hydrogen, which is 1. Okay. Therefore, if you consider that all these relative masses are given with respect to hydrogen, we are okay with that. Okay. We can run with that. It works for all government purposes. Okay. So all the relative mass, in other words, okay, the relative masses in the periodic table are presented with respect to hydrogen. Hydrogen is 1 with respect to that. Helium is 4 times more massive. Carbon is 12 times more massive. And oxygen is 16 times more massive. That's what it says. Okay. And these are the elements. Now let's say that you have a compound, chemical compound, which has more than one element, obviously, like H2O. If you want to know the relative mass of that, what do? You add the relative masses of 2 hydrogens, 2 times 1, to the relative mass of oxygen, which is 16. So 2 times 1 is 2, plus 16 is 18, and that's how we know the relative mass of H2O is 18. Let's take another example, CO2. Okay, CO2 has carbon and 2 oxygens. The relative mass of carbon is 12. To that, we're going to add 2 times the relative mass of oxygen, which is 16. 2 times 16 is 32. 32 plus 12 is 44, and that's how we get the relative mass of carbon dioxide. Okay, this way, we can determine the relative mass of any particle that is given to you if we know the composition. All right, now let's check this out there, okay? And this time is your turn. Here are some substances. I want you to determine the relative masses of these substances. Go ahead. Okay. Under each symbol, you should be able to find the relative mass of that element. Okay? So that's what you need to do. That's it. I'll even open a periodic table here. All right. And here are our responses. These are really good. And these are the correct answers as well, 98%. So based on these responses, I would say that we have achieved the first learning objective. Okay, meaning determining the mass, relative mass of any given particle based on the composition. We can do that now. Okay. Yeah. Now let's move on to the next phase. Okay, we are going to get into the concept of molarity or molar. Okay, mole or Avogadro's number and stuff like that. That's what it's going to be. That's what we're going to be doing next. Yeah. So let's say that you went to the lab and then measured 6.94 grams of lithium and 9.01 grams of beryllium and 22.99 grams of sodium. Okay. My question is, which sample do you expect to have more atoms? By the way, these are the relative atomic masses of each of these elements. Okay, you are taking the gram amount of that. That's what you've done here. Okay, so I'll open the question. And then I'm going to interrupt you again in about 30 seconds to force you to think about something.
Like how to do this. Essentially, okay. Maybe not like explicitly saying that, but yeah, so you would divide,
I will read this question in a second, okay? But before that, I want the answer for this question. Say that an orange is 5 times more massive than a grape. One more time. An orange is 5 times more massive than a grape. Okay? If you take 5 grams of oranges and 1 gram of grapes, do you have more grapes or more oranges? Anybody? Everybody? I didn't hear you. One more time. An orange is 5 times more massive than a grape. Okay? If you take 1 gram of grapes and then 5 grams of oranges, do you have more oranges or more grapes? It's going to be the same amount. Thank you. Okay? That's the idea of the relative mass. Let me ask another question. You take 100 grams of grapes and 500 grams of oranges. What do you have more, grapes or oranges? It's the same again. Yeah, that's the idea being tested in this question as well. All right, I'll reopen the question in case somebody wants to submit the answers.
basically it's the pair.
Right.
So if
We have more than 90% responses.
just like 5 times that.
Therefore, I'm going to close this question in 5, 4, 3, 2, and 1.
That's. Like we have 1 grape and 1 orange, right? You just compare them like.
Okay. Now, here's a question for you. Now, we know they contain the same number of particles, same number of atoms. But how many? Does anybody know? How many will they contain? What is this number? Does anybody know? Yes, sir. Can I have the microphone there, please, Peyton?
I think it was,
Yeah, what's the name? Say one more time.
was it 6.022 times 10? Oh, the name?
Yeah. That's the number as well. Yes, name first, yeah.
My name.
Yes.
Okay, Leo.
Thank you, Leo. 6.022 times 10 to the power of 3. In other words, that's the idea of Avogadro's number. That is also known as the Avogadro's number. Okay. So let me reiterate what we just did here. If you get this place, is really important. If you take the gram amount of the relative mass, it will contain Avogadro's number of particles, or 6.022 times 10 to the power of 23 particles. Okay. Oh, by the way, so this number is huge, right? Every time we have, if you have to say like 6.022 times 10 to the power of 23, it's really hard for our tongue and everything. Okay. So there's a little shortcut. Maybe a shortcut. I don't know. Okay. It's just like this. So remember, sometimes you go to grocery stores and then buy eggs. If you buy 12 eggs, we call it what? A dozen of eggs, right? Just like 12 is 1 dozen, 6.022 times 10 to the power of 23 is 1 mole. Yeah, that's the idea of 1 mole. So 1 mole contains 6.022 times 10 to the power of 23 particles. Just like 1 dozen contains 12x, 1 mole contains Avogadro's number of particles. Okay, and that's the idea of the mole. And also, we know the gram amount of the relative mass contains 1 mole of particles. Okay, and that also has a special name. The mass of 1 mole is also known as, what do you think? Mass of 1 mole is known as? Somebody should know this. Mass of 1 mole is known as? Anybody? Leo, anybody? Anything? Yes, sir. Molar mass. Yeah, that's called molar mass. Yeah, so that's the idea of molar mass. So we went through the idea of the Avogadro's number, and Avogadro's number of particles is 1 mole, and the mass of 1 mole is the molar mass. Okay, so now let's do this. Let's say that we want to find the molar mass of any substance. Okay, let's start with what we see in the periodic table, like carbon. Okay, if somebody asks you the molar mass of carbon, you go to the periodic table, read the number under that symbol of carbon, which is 12 point something. That's the relative mass of that. And you take the gram amount of that, and that contains 1 mole of carbon atoms. Okay, therefore, the molar mass of carbon is 12 grams per mole. 1 mole is 12 grams. Yeah, just like that. Let's say go to different element like sodium. Okay, relative mass of sodium is 22.99. If we take that many grams, that contains 1 mole of sodium atoms. Okay, so the molar mass of sodium is 22.99 grams per mole. So the molar mass has these units, grams per mole units. The relative mass, sometimes they don't write units, but sometimes you see that they write AMU, atomic mass units, for relative mass. Okay, just for our information. All right, so these are for just single elements. Okay, but if we have a molecule like this is chlorine. Okay, so you have 2 chlorine atoms here, meaning 1 chlorine is 35.45. Relative mass of 1 chlorine atom is 35.45. So because Cl2 has 2 of them, we're going to multiply that by 2, and that gives us 70.9, right? So 70.9 is the relative mass of chlorine. If you take the gram amount of that, that contains a mole of Cl2. So that's the molar mass of chlorine. I want you to do P4, but maybe on the next page. Do we have any questions so far before we do an activity on this? Anything? Let's do an activity. I'll walk around. You can ask me questions while I'm walking around as well, okay? All right, let's do... Oh, wait. Before we do that, okay? We can do the same thing for chemical compounds as well, right? The relative mass of H2O is 18. You take the gram amount of that contains 1 mole of H2O. So therefore, the molar mass of H2O is 18 grams per mole. And carbon dioxide is 44 grams per mole. Same thing. Okay. All right. With that, let's try this. Here you go. And then we're going to do some practice problems. Two and 1. And here are our responses. Okay, it's mostly good. These are the correct answers. Okay, it can be better though. Okay, so I'll do the last one. We have 6 carbon atoms, so 6 times 12 plus we have 5 plus 2, 7 hydrogens, so 7 times 1 plus we have 1 nitrogen, so 1 times 14. Okay, 6 times 12 is 72. 72 plus 7 is 79. 79 plus 14 is 93, right? Okay, so the relative mass of This compound is 93. You take the gram amount of that contains mole of this. So the molar mass should be 93 grams per mole. Okay. What questions, concerns, comments do we have? Okay. If you are given the molar mass, if you're given the composition of the particle, like the formula of the particle, okay, we should be able to determine the molar mass of the same. So let's do this. Let's do some real problems with this now, okay? So far we were just, touching the surface. Now let's get into this. I'm gonna actually hopefully dive into this with problem like this, okay? Now, before you start the problem, okay, I'm going to do something for you. I'm going to organize the only two equations we're going to be needing to solve these problems. And then I'm going to show you two methods to solve problems like this, okay? It goes like this. Let me go to my notebook. Okay. So the first thing is this. Oh, by the way, if I buy 18 eggs, how many dozens am I buying? How many? If I buy 18 eggs, how many dozens of eggs is that? 1.5 dozens. Okay. So how do we get that number? Remember? Okay. So I'm buying 18, right? Now N is 18. And then number of eggs in a dozen is 12. Therefore, the number of dozens is number of eggs divided by the number of eggs in a dozen. So 18 divided by 12, and that's how we got 1.5 dozens. Okay. Now, similarly, if somebody asks you for the number of moles, we do the same thing. So we have N, okay, and then divide that by the number of particles in a mole, Avogadro number, and that gives you the number of moles, lowercase n. So here the lowercase n is the number of moles, uppercase n is the number of particles, and then n sub a is the Avogadro's number. You can write 6.022 times 10 to the power of 23 per mole. So you should put this in a box. This is the first equation we'll be using for these problems. Okay. And then the only other equation we need is the molar mass. Okay. So the molar mass is mass divided by the number of moles. Okay. Or if you want to, you can rearrange this, but I'm going to leave it like this. So here the uppercase M is the molar mass, and then lowercase m is the mass, and then N is the number of moles. You can rearrange these equations any way you want if it helps you. Okay, these are all the equations we're going to need. Now, when you're given a problem, like in this case, you are given the number of particles. I think it was 5 times 10 to the power of 21. I think it was 21. That's what is that was what was given to you. Okay, and then they are asking for the mass of oxygen. Okay, so they are asking for the mass. Okay, and what do we know? We know the Avogadro's number, 6.022 times 10 to the power of 23 per mole, and we also know the molar mass of oxygen, which is going to be 32 grams per mole. This is what we know. Now we cannot go directly from number of particles to mass. Okay, first thing we need to do is when we have N, we need to convert that to number of moles, and then number of moles we need to convert to mass. There should be 2 steps like that. So step 1, step 2. How do we get number of moles, lowercase n from uppercase n? With first equation over here, you can see that number of moles is n divided by the Avogadro's number. That's number 1. That's the first step. Okay. And then if in the second step, you want when you have the number of moles, you should be able to calculate the mass, because we see that mass is equal to number of moles times the molar mass. I just rearranged this. I just moved my n to the other side. So mass, lowercase m, is equal to number of moles times the uppercase m. Okay? And that will give you the mass. All right, I'm going to let you play with this for a minute, and then I'm going to solve this myself in two ways. This is the first one I'm going to do, and then I'm going to do another one. Go ahead. Okay, but I'm going to show, I'm going to do this myself with you, okay? I already have the numbers. I just need to plug and chug. I don't have a calculator, so that's my excuse. All right, so every time you are asked the mass, and then only given the number of particles, you need to calculate the number of moles. Okay, just keep that in mind. Anyway, so therefore, if I plug in the numbers, uppercase N is 5 times 10 to the power of 21, and the Avogadro's number in sub A is 6.022 times 10 to the power of 23 per mole. And this gives me about 5/6 times 10 to the power of -2 moles. I don't have a calculator, that's why I did it like this. But you can actually, plug in these numbers to a calculator and then get an actual number. But I don't have a calculator, so I'm going to leave it like this for the moment. Now I have the moles. Now, to get the mass from the moles, all I have to do is plug into this equation. Mass is equal to number of moles, which is 5/6 times 10 to the power of -2 moles, multiplied by the molar mass, which is 32 grams per mole. So moles cancel out. I'm going to get the answer in grams. Can somebody tell me what you got? 0.27 grams. Okay. So this is one way. There's another way. Okay. I've seen that people try the second way better. I mean, prefer the second way more than the first way. So let me show you what I mean by that. So in the second way, you don't care about these equations that much. Okay. You only care about canceling out the units until you get your preferred units. Okay, like grams in this case. Here's how it goes. We always start with what is given, which is n. So let me write like this. So you are given the number of particles, which is 5 times 10 to the power of 21. But I don't want that. I want grams. So I'm going to get rid of the particles. I know the Avogadro's number, which is 6.022 times 10 to the power of 23, okay, has the number of particles. Okay, this is how many particles we have in 1 mole. So if I do that, the particles cancel out. You're going to end up with the units of moles. But I don't want moles. I want a gram. So I want to get rid of moles. So to get rid of moles, I'm going to have moles in the denominator. I know 1 mole of oxygen, okay, is 32 grams of oxygen. Yeah. So here the moles will cancel out. Okay. And then I'm going to have the grams of oxygen, and that's it. So you can see that just like in this equation over here, we have 5, 10 to the power of -2, and 32 in the numerator. Let me zoom in. Oh, that's zooming out. Okay. Just like that, I have the same numbers here. Okay. And in the denominator, I have 6.022 because I did not change anything. All right. It's the same thing. And if you plug and chug these numbers to a calculator, you should get 0.27 grams of oxygen. Same thing. All right. Any questions, concerns, comments? Let's do one more, okay? One for the road. One for the road. You can get from this area. In my experience, usually, things are going to get easier. It's going to be downhill from here. I mean, once you get through something like this. Okay. So I started with them so that you have already seen the words. Now it's going to be much easier for you after that. All right, so because of the time constraints, I'm going to do it like this. I'm going to do this on my screen with you. I need your help now. Everybody, I want your attention, okay? So always, I'm going to do the second method now so that I can finish the question just one line. That's the goal. Okay? That's our dream, yeah? So start with what is given. You are told that drinking 2 liters of water. If you don't, you should drink 2 liters, okay? 2 liters means 2,000 milliliters. We know that, okay? So that is what is given to you, okay? And then they are asking for the number of molecules. They are asking for N. They are given the volume of water we drink. That's what is given, okay? So anyway, I don't want milliliters, so I want to cancel it out. So what do? I'm going to divide this by milliliters. I know 1 milliliter of water, according to the question, is 1 gram, contains 1 gram of H2O. 1 milliliter of H2O is 1 gram of H2O. If you don't believe me, I'll show you. Okay, so here 1 milliliter of water is 1 gram. I just used that. Okay, why did I do that? Cancel out milliliters. Now I have grams. I don't want grams. I want to get rid of the grams. Okay, what do? I'm going to divide this by 18 grams of H2O. Why 18? I know 18 grams of H2O is the molar mass of that contains 1 mole of H2O. Okay, when I do that, grams of H2O cancels out. Now I have moles. I don't want moles either. I want the number of water molecules or particles. Now to do that, I want to get rid of moles. So I know 1 mole of H2O. I have this hole here. Okay, H2O contains 6.022 times 10 to the power of 23 molecules of water. So when I do that, most of H2O cancels out, and you're going to get the molecules or the particles of water. That's it, you're done. You plug and chug these numbers onto a calculator, okay, and then you're done. That's it. All right, so bring your calculators, okay? So, I don't care whatever that is, bring your calculator, and that's gonna, you can use that. I need to open the attendance code. What's the answer? Does anybody know? What is that? A? Option A. That's what I was told, okay? So let me do this. I'm gonna close. Yeah, the correct answer is A. Okay, wonderful.